Okay, so far we have seen that this code behaves properly and can generate random solutions for us, can evaluate them, make sure that they are feasible, and if they are feasible, calculate their objective function, and also updating the best solution and the best value that we are actually looking for at the end of this code and or the pseudocode. This is what we are actually looking for. So the other thing that we can do to also analyze the behavior of this code and make sure that it operates properly is to, let's say, instead of having this line of code here that we generate random solutions, we just actually make them a comment, like deactivated them, and import the solution by ourselves. Okay, so for this to happen, and so every time that we are just giving one possible solution to the code and see how the code is going to evaluate that one. So let's, for this one, I'm going to copy paste this part because we are not going to go, we don't have an iteration, so we are not going to update this one. So if we copy paste this line of code and in another cell, so, and therefore we need to select all of them, and then we can press shift and tab at the same time so they go back in your screen, so you just get rid of those you know spaces. So here we have, so that we set the total weight is equal to 0, and then we are updating the total weight for the value, the W, and we also have the total value for V. So what I need also here is these three things, and also I think I need N also, but let's do this. So I'm going to have this one, we have W, we have C, and we also need N, so we know that N is equal to the length of the W or V, whatever you prefer. And then what we need to do here in this line of code is actually giving or producing some solution by ourselves. So the variable that we used previously was X, so I'm going to have X equal, which is going to be a list. So far we need, so let's say we have zeros, we have 5 zeros, which means that this is one of the extreme points. Okay, so the thing that we do here is actually using the values that actually we can calculate the objective function easily, and we are sure that what should be the output of the model based on them. So for example, for this one, we are sure that the objective function should be equal to 0, okay? And it should be feasible because the total weight is equal to 0, so it should be feasible. So if I run this line of code, so the total weight is 0, the solution is feasible, and the total weight is also equal to 0. So we have that thing. So this is, which means that the code works properly. And then the other solution, the other extreme, is when all of them are equal to 1. So if I put them, make them equal to 1, we know that the summation of the weight, definitely based on the vector, based on the list that we have here, it's definitely the summation of them is more than 10. So this solution should be infeasible. So if I do that, if I run this line of code, the total weight is 21, and therefore it didn't even go to this part to print the solution is feasible and calculating the objective function. So this is also behaves properly. So now that I have this one, one thing that I can do is starting playing with C, for example, the parameter that I have. So if in this case, if the total weight is 21, so if I make this C equal to 22 or any number greater than 21, which means that solution should be a feasible solution. So I go to the C, and instead of 10, I'm going to type 22. So in this case, I should expect that the code consider this solution as a feasible one, and then since this is feasible, print the solution is feasible and also calculate the total value for us. So if I run this line of code, now this 21 is a feasible solution and the total value is 46, which is the summation of this list. Okay, so this is also shows us that the code works properly. Okay, the other thing that we can do is we can go back to this line of code. I'm going to get rid of those print. I don't think, I'm just going to make them comments, so maybe I need them later, but yeah, I don't need this one. I actually don't need this one, and here we don't need this 2 lines also. So this is actually what we get from the AI, in our case ChatGPT, and the C is equal to this one. So one thing that I'm going to do here is to make the same thing. So we have max trial is equal to 10, and I'm going to make C a large number. You see, the total sum of those values is 21. Okay, so if you can put here 100, 1000, whatever you want, but as long as this number is greater than 21, greater than or equal to 21, you expect that a solution that has all of the items should be chosen, because this means that the total capacity is less than the maximum capacity that you have. So I'm going to set it to 21, and because we check if this is less than or greater than C, so 21 is also make that solution feasible. And then I'm going to run this line of code, and if I run this one, we see that all the solutions are feasible. If you remember from the previous recording, when we had 5 iterations, when we had 5 different solutions, the fourth one and the fifth one weight was 14 and 11, and so those two were infeasible when C was equal to 10. But now, because we set C equal to 21, so all of those 10 solutions are feasible, and so the best value is 46, as we see here, when all of them are equal to 1, x, all of them are equal to 1, so the total weight is 21 and the best value is 46. Now, in this line of code, the best solution is when all of them are selected and the best value is 46. So again, this works properly. Now let's do something else. We check another edge here. C was equal to 21, which is the maximum, and let's say C is equal to 0. The capacity is nothing. So we expect that all the solutions except one, when we don't choose any of them, should be infeasible. Let's run this line of code, and here is the case. Except one, when all of them are equal to 0, the solution is feasible. All of them are infeasible. And the best solution is none. We don't have any best solution, and the best value is also equal to 0. So there's something here. So if the total weight is less than or equal to C, which is in our case, so yeah, this is the thing. Because we don't have equality here, that's why this solution is not the best solution. Okay, in this case, so for example, if I said if the total value is greater than or equal the best value, then I expect that this one should be the best solution. Let's do this. Okay, let's make it greater than or equal. So in this case, this solution to this expression 0 is greater than or equal to 0 is true. Previously, when we don't have this one, 0 is greater than the 0, so the answer is false. So we didn't update the best solution or the best value. So make it equal to 0. Now 0 is greater than or equal to 0. So this is true. So we expect that the code is going to update the best solution and also the best value, which is still 0. Let's run this line of code, and here we go. Again, the second one is all zeros, is the only feasible solution, and finally at the end we have the best solution equal to 0 and the best value is also 0 as we expected. So let's change this one to this and change C to 10 as it was. Okay, now let's run this line of code, and let me do something for you here and activate this line of code. Or no, not this one. I'm going to activate this one, print the best solution and also the best. We don't need the best solution, but I'm going to show you both of them here. So let's run this line of code again. Okay, now we have 10 trials. We have 10 different solutions, and what I wanted to show you here is that, so we start with this first solution, we check the feasibility, and then the current best value is 14. So what was the best value at the beginning? The best value was 0, and now the best value is 14. What we expect from this block of code is that we only update the best value if the total value, which means the current solution is actually better than what we had so far. In this case, we are going to update the best solution. So what I wanted to show you here is that the value of the best solution is always increasing. What does it mean? We never, for example, if we start from 0, we go to 14, we shouldn't go back to 10 or any number less than 14 because of this line of code that we have. So all the time we expect that the values of the best value are increasing. Okay, so it starts from 0. Now we have 14. The next time that we updated, the current best value is 15, which is greater than 14. The next time, this is 24, which is again greater than 15, so and so on. Okay, so all the time the solution, the values of the best value are increasing. Okay, and here we go. If I'm going to do something here and make this C again equal to 21, so I expect that all ones are going to be a feasible solution, and if I run this line of code, we can see that we start again for the best value, start from 0, the first time updated 14, then 15, then 29, and then 46, and because the 46 is the maximum that we can have, we are not going to update this 46 again, and so the final value for the best value is 46. Okay, so this is the other thing that we have to make sure in case that this one is greater than we have this condition in our code. We have to make sure that all the time the behavior or the values of the best value are increasing. Okay, and finally I'm going to do something. I think 10 is enough, but let me increase the maximum trial to 20. Put this maximum capacity back to 10, and we also didn't change anything here, so yeah, we are good here. So one thing that I wanted to do is that we have 20 trials. I'm going to change the values of W and V. So imagine that you have an item that its total weight is 0, okay, which means, let's say, could be a little lame here, but since we are going to have the Valentine in less than 3 weeks, less than if your significant others is going to accompany you in that hiking trip, so you don't need to carry him or her, and so the total weight is going to be equal to 0. And then the value of having him or her with yourself is going to be, let's say, too much. We are going to add 20. Okay, so in this case, this item, which means the last item, the weight is 0 and it has the highest value here. But we expect in 20 trials, since we are generating random solutions, for this one to not be chosen and not be in the solution should be 0.5 to the power of 20, which is a very, very small number. So in this case, having an item that has actually no weight comparing to the rest of them and has the highest value, we expect that after 20 trials, this one should be in the solution, because the chance of not choosing this item, which means that every time that we're generating this one is going to be 0, is 0.5 to the power of 20, which is a very small number. So let me run this line of code and see what is happening here. So again, we start from 14, we update it to 15, we have 26, and we have this item here for the first time. It shows up here, and we had 26, then we had 43, and we still have this item here, and 44, and finally, and the best solution that we can have is actually equal to 44, and this solution is also there. So I just wanted to show you that, for example, we can expect if we have an item that its cost benefit is so in favor of the problem. In this case, there is no weight, but the value is the highest among all the items. We actually, after quite a number of trials, we should expect that this one should always be in the final solution, because this is the best that we can have as an item in our knapsack, for example. So with this, again, just to show you, just to summarize what we did in this recording, is that we tried to give solutions, actually the edges. We tried with all zeros and ones here and see how the model behaves, and then we tried to change the capacity, the maximum capacity of our problem. We set it to 0 and see that all the solutions are, except one, when we don't select anything, are infeasible. We also see that if we set C to a large enough number, all the solutions could be feasible, because if C is set to be greater than or equal to the summation of the total weight. And then what we tried here is to change the C, or the capacity, in this line of code, which is our actual code that we generate random numbers, random solutions here, which is it's actually our algorithm. It's our random search algorithm for the knapsack problem. We also played with C. We set C to 0, we set C to 21, and we also see that if we have an item that is its cost benefit it is in favor of the problem, we can expect that it's going to be in the final solution. So with this one, I conclude this recording, and I hope to enjoy it and see you next time.